Okay, now we're going to talk about actually calculating the pH of a salt solution. For a solution of a salt in which only one ion hydrolyzes, the calculation of equilibrium composition follows that of just of a weak acid or a weak base. Now, we're not going to deal with two ions in this class, so everything's going to be one ion will ionize, or neither one will ionize. So it's either going to be neutral, acidic from the cation, or basic from the anion. Major difference is going to be that you're going to have to first figure out your Ka, Kb through the Kw, okay? Because typically all your K is going to be given from molecular substances. So if you're dealing with a salt, you're going to have some ion that actually undergoing hydrolysis, so you're going to have to make that conversion. But the rest of the calculation will be the same. You set up your equilibrium. Once you see equilibrium, you write your ice table. Ice table, calculate your K, making sure you're using the right K. Solve for X, solve for pH. Before we actually do a calculation, I want to refresh our memory of what we're doing here on our thought process on calculating pH. What I'm doing is trying to get you set up to do the harder problems, which are later on where you do a neutralization. So I'm trying to make everything look exactly the same. If you follow my process and ask yourself questions along the way, then you're going to dictate to yourself where to go next. If you follow the process, it's a really easy thing to calculate the pH. Okay? If you don't follow the process, then what's going to be is going to be very hard and time-consuming and confusing to figure out the pH, because it takes a lot of calculations to get that final answer when you're dealing with a neutralization. This is the same process that you can use even when you get into quantitative analysis. It will still give you the same flow diagram to basically get to the final pH, even if you're dealing with dye products, etc. So what we're doing is we're going to say, first off, you're going to ask yourself a question. Okay. Is the reaction, is it a reaction or is it a single solute? Why I want to ask that? Well, basically, if it's a reaction, I know I got to do more work before I get to what I've been doing. Okay. As we move along in this, we add more and more work before we get to what we did a long time ago. Okay. So if it's a reaction, I got to do more work. If it's a single solute, now I'm in that area of what we've been doing. Okay. Next, is it an acid or a base or a salt? If it's an acid or base, I know how to handle it. That's if it's strong, it's a straightforward calculation. Okay? If it's weak, I know I got to do a Ka problem, set up my ice table and calculate. If it's a salt, though, now I know I got to write the dissociation and examine the cations and anions in both, okay, to determine if I got an acid or base hydrolysis. And then we're talking about a Ka or Kb problem. So we can set this up in a little diagram here. So what I'm saying is, first question is it single solute or reaction? If it's a reaction, then I got to do a neutralization. Haven't covered that yet, but we will. But it doesn't matter. As soon as I finish neutralization, then I'm back to the same spot as if I did a single solute. Okay? I'm at the point now I got to look at and say, do I have an acid or base or salt? Okay? So after I do the neutralization, I'm back to looking at the species and figure out what do I have to dictate my pH. If it's an acid or a base, we know I got to look at it in terms of strong or weak. If it's a salt, then I got to look at it in terms of soluble or insoluble. Now, we handled soluble, but we didn't handle insoluble yet. That'll be happening in another chapter. Next question is it strong? If it's strong or weak, we got to decide how do we handle it? Well, if it's a strong species, we know that it's 100%. Straightforward calculation, the easiest one we got. Okay, same thing for a base. If it's a strong, we know it's 100% ionization, straightforward calculation. If it's weak, then I got to do my Ka, Kb. Okay, basically you write your equilibrium, you do your ice table, solve for X, solve for pH. Okay, that's for your weak acid or weak base. Difference between acid and base is that we can end up X being hydronium for the acid and X will be hydroxide for the base, which is a different calculation for the actual bottom line pH. If it's a soluble salt, then we got to look at the cation and anion separately. Okay, because they can determine the acidity or basicity of a solution. Okay, so if it's a cation, we say, okay, is that one of the cations of the strong bases? If it's one of the cations of the strong bases, it's neutral. I don't have to worry about that cation. Otherwise, I got to worry about the cation, and we got a Ka problem. Equilibrium, ice table, solve for X, pH. Then we look at the anion. Is that an anion of the monoprotic strong acids? If it is, then it's neutral. Don't have to worry about that part. Otherwise, yes, I got to worry about it. There's a KB problem, which means write the equilibrium, ice table, solve for X, pH. If it's insoluble, then I'm talking about a KSP problem. That's going to happen in another chapter. But this is basically the flow diagram. If you buy into the flow diagram of what I'm doing, then all these problems look very similar and they're all very easy. Okay? If you try to make all these problems look different, that's when it gets confusing. I'm trying to make them all look the same, and what's going to dictate what you do is you ask yourself questions and go on. Now, I'm not going to be in your head, basically, when you're taking a test or trying to solve this, so you need to ask these questions to yourself and have the flow diagram go. And you should basically be taking notes right now and why we're doing certain things and writing that down so you can get that in your head of what do I do next on my own to solve this problem. So here's an example. What is the pH of a 0.1 molar solution of sodium cyanide at 25 degrees C? The Ka of HCN is 4.9 times 10 to the minus 10. So the first question we're going to ask ourselves is it a single solute or is it a reaction? It's a single solute. We haven't handled reactions yet. What's the next question? Is it an acid? Is it a base? Or is it a salt? Okay. Salts are those things that are metal, non-metal, metal polyatomic ions that don't involve hydroxide, oxide, and hydrogen, okay, as the anion. So this is a salt. Well, since it's a salt, I want to go a little deeper in that question and say, okay, is it acidic, basic, or neutral salt? Why? Because I want to be able to answer that last question. Does the answer make sense? Well, we're looking at this. Sodium, is that one of those cations that we memorized as being neutral? Yes. So I don't have to worry about that. Is cyanide one of those ions that we memorize as being neutral for the anion? No. So therefore it's adding base to it. So this whole thing then is what type of salt then? A basic salt. Since it's a salt, my next question is it soluble or insoluble? Okay, I want to know, is it soluble or insoluble since it's a salt? Because if it's soluble, then I'm going to go on, the first thing I'm going to do is go directly into writing a dissociation. Anytime I got a soluble salt, I write the dissociation and go on with the rest of the problem. In this case, it's a soluble salt. So the first step I'm going to do next is I'm going to write the dissociation of a soluble salt. Okay, because I need to do that for any type problem I'm going to do for the rest of the stuff, be it neutralization, whatever. I want to know what's going on there after that. So we know that I have 0.1 molarity of sodium cyanide. Well, since it's a soluble salt, how much does it break up? 100%, which means then I have a 1-to-1 mole ratio between sodium cyanide and sodium, which means I got 0.1 molarity, and a 1-to-1 between sodium cyanide and cyanide ion, which means I got 0.1 molarity. Notice if I had some subscript, like CN with a subscript 2 behind it, then I would have 2 cyanide atoms, which means I would have to multiply by 2. I got to account for the number of ions. We already said that sodium is neutral, so I don't have to worry about that. But cyanide, we said, is something that can undergo some hydrolysis. So what's my next step after I realize that cyanide can be changing the pH of that solution? Yes, I have to next go ahead and do my hydrolysis. Okay, so I write my Cn minus plus water. Cn is my base, so my acid is water is going to donate the proton, which gives me 8Cn and OH minus. Okay, it's producing OH minus, which is a base. Once I write my equilibrium, my next step is an ice table. So anytime I have an equilibrium, then I'll do an ice table. So I have my initial, my change in my equilibrium. I have 0.1 molarity of cyanide. I have 0 of hydrogen cyanide and approximately 0 for hydroxide. Remember the water that we've been neglecting. Now, an important point here is you got to realize that I got 0.1 cyanide. Since I gave you the Ka, sometimes people want to flip the reaction and change the HCN to 0.1. You can't do that because that's not what I have. I have 0.1 Cn minus. That's what I have, and I have to deal with that. I can't change it to fit the Ka that was given to me. Okay, so I need to work the problem as it's given to me. I know that I have 0.1 molarity of cyanide. Okay, next I have to decide which way this thing's going to shift. Well, that's, as we say with all this acid-based stuff, it tends to always go to the right. We're going to point to that 0. Okay, so it's going to go to the right. So if it goes to the right, that tells me that I got minuses on my reactant side and pluses on my product side. Then I need some relationship of change. I don't know how much it's going to do, so I'm going to pull out of the air X, and everything's 1 to 1, which we said most of this acid-base stuff's going to be. So I have X, X, and X, and add them up. I get 0.1 minus X, X, and X at equilibrium. The next very important question that you have to ask yourself is, how are these three things related? Well, I'm talking about cyanide, which is a base forming hydroxide ion. So how is 0.1 minus X, X, and X related? They are related through what? Kb. So then I have to set up my Kb expression, which would be my products over reactants, which would be my hydrogen cyanide times my hydroxide ion divided by my cyanide ion, and that's all equal to Kb. So when I start plugging in my numbers, I plug in my X for the hydrogen cyanide. I plug in X for my, I plug in X for my hydrogen cyanide, my X for my hydroxide, and 0.1 minus X for my cyanide ion. But then the question is, what am I plugging in for Kb? What was I given in this problem? I was given Ka for 8Cn. I need Kb for Cn minus. Okay, what are we going to have to do to fix that? Yes, we're going to have to go through Kw to fix that. It's an important problem. This is where a problem can happen. This is where careless error can happen, which is going to change your final result, which sometimes by asking the final question, does this answer make sense, lets me catch those careless mistakes. So Kb will be equal to Kw over Ka, which is 1 times 10 to the negative 14th, divided by 4.9 times 10 to the negative 10th, which is equal to 2.0 times 10 to the negative 5th. Plug in my values, which are x, 0.1 minus x, which gives me x squared divided by 0.1 minus x. Now I can move into the quadratic formula, or I can try to simplify this. We said we can simplify this by looking at your powers of 10. Okay, 0.1, that's the same thing as saying 1 times 10 to the negative 1. Okay. Comparing that 10 to this 10, that's 4 10s difference. We said if it's 3 or greater, we can neglect x. Okay. We also compare the concentration to the Kb in this case, and if that's greater than 100, we also said that we can neglect the x. In both cases, we're talking about yes, that is the case. So I can basically then say, okay, I can neglect that x. Okay, and change my math now to x squared over 0.1 is equal to 2.0 times 10 to the negative 5th. Multiply through by 0.1 on both sides, which gets me x squared is equal to 2.0 times 10 to the minus 6. Take the square root of both sides, which gets me x is equal to 1.4 times 10 to the negative 3rd. Another important question I got to ask myself now, what does x represent? On our problem, our equilibrium and ice table, what do we have x represented on those product side? It's equal to the hydroxide ion, as well as it's equal to the hydrogen cyanide ion. Don't really care about the hydrogen cyanide in this issue. All I care about is hydroxide. If I'm talking about a base hydrolysis, that x is going to be equal to hydroxide. If I'm talking about an acid hydrolysis, that x is going to be equal to hydronium. This is where an error can happen. You got to make sure you got the right x for the right component for that x. So how do I calculate pH from here? Well, I'm going to go by my equation that I explained before. I'm just going to, because on a calculator, I already have 1.4 times 10 to the negative 3rd on my calculator. So I'm just going to take the log of that and add it to 14. So I'm using my little pH calculation that I do for a base, which is pH is equal to 14 plus the log of hydroxide concentration, which is equal to 14 plus the log of 1.4 times 10 to the minus 3, which is equal to 11.15. Now, at this point, I want to ask myself one more question, which is what? Does it make sense? Well, we said that this is a basic salt, so what kind of pH do we get? A base. So I have a chance of being correct. It's at this point here, if I got an acid pH, that I made one of those careless errors. I could have used Ka instead of Kb. That's going to flip-flop it. I could have called it hydronium instead of hydroxide. That could have flip-flopped it. Now, There is the problem if I make two mistakes. Well, they could cancel out each other in the sense of I still get a basic pH and still be wrong. Okay, two wrongs don't make a right. Okay, so what could happen is you basically flip-flop your Ka, Kb, flip-flop your hydronium hydroxide, still get a basic pH, but your answer is going to be wrong still. Okay, now if you do one of these errors, then what's going to happen? It's going to give you the pH, the opposite pH. Okay, so if it's a base, it's going to end up being an acid because you flip-flopped. But it's just good to check your answer to see if you got a chance of being right and see if you did make one of those careless mistakes, and maybe you can fix that. Okay, in your final answer. Let's do another problem. Well, what is the pH of a 0.1 molar solution of ammonia iodide? Okay, I'm looking for the pH of a 0.1 molar solution of ammonia iodide. Well, we go through our process. Single solute, or is it a reaction? Single solute. Next question. Acid, base, or salt? Answer, salt. So it's a salt. I want to know if it's acidic, basic, or neutral, for I have an idea where I'm heading with this. Well, we know that the ammonia is an acidic component, and the iodine is a neutral component, so my whole salt is what then? Acidic. It's acidic salt. Well, since it's a salt, my next question is what? Is it soluble? Is it insoluble? In this case, we're talking about a soluble salt. That's important to me because now, since I know it's a soluble salt, my next step will be to write the dissociation of that salt. So I'll write the dissociation of the salt. We know I got 0.1 molarity of my ammonia iodide. I know it breaks up into ammonia and iodide ions. Since it's a 1-to-1 between ammonia and ammonia iodide, it's 0.1. Since it's a 1-to-1 between the iodide and ammonia iodide, it's 0.1. Once again, if I had some subscript, I would have to account for that. We already said that the iodide I don't have to worry about. Okay, so this ammonia is the one that I got to worry about for the pH of the solution. So where do we go from here? Well, I got to take that ammonia ion and do my hydrolysis. So I write my hydrolysis. So I have my ammonia plus water. This is my acid component. So it's going to donate the proton. Okay. So that leaves me with NH3 and H3O+. Since this is an acid, it should be giving me hydronium ion. Once I write an equilibrium, then next step will always be write an ice table. So I do my ice table. I know my initial is 0.1. That's coming from my soluble salt. So this is coming from that soluble salt. Okay, that's where I'm figuring out that one. I'm from that soluble salt. Approximately 0 for my hydronium and 0 for the ammonia. Which direction does this reaction have to go? It's going to have to go to the right. Okay, which means then I have negatives and positives on the product side. I need some relationship. Let's call it X. So it's X, X, and X. Add them up. That gives me 0.1 minus X, X, and X for my equilibrium. Next important question is, how is 0.1 minus X, X, and X related? How are these things related in this problem? I'm talking about NH4+, which is an acid producing hydronium ions. So what kind of equilibrium are we talking about here? Yes, a Ka. So I'll set up my Ka. Be my hydronium ion concentration times my ammonia concentration divided by my ammonia ion. But notice in our reaction, what were we given? We were given what in our equation? Kb of ammonia. So do I just take the Kb and shove it in there because that's what's given? No. I need Ka of my ammonia ion. Okay? So I need to use that value. I was given the Kb of ammonia. So I need to fix that. How do we fix it? Through Kw. Which means that Kw divided by Kb will give me my Ka, which is 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, which gets me 5.6 times 10 to the negative 10th. Plug in my values for hydronium, ammonia, and ammonia ion, which is X, 0.1 minus X. That gives me X squared divided by 0.1 minus X. Now I want to simplify the equation if I can. So what are we going to do? I'll compare my concentration of my acid to my Ka. Notice that there's 9 powers of 10 difference. So can I eliminate the x? Yes, by a long shot, which basically means I can get rid of that minus x, which leaves me at x squared over 0.1 is equal to 5.6 times 10 to the negative 10th. Okay, mathematically, next, multiply by 0.1 on both sides, which gets me 5.6 times 10 to the negative 11th, square root. X is equal to 7.5 times 10 to the minus 6 molarity, which right now, my next question is, what does X represent in this problem? And you can see X represents in this problem my hydronium ion concentration, as well as my ammonia concentration. Don't care about the ammonia in this problem, but I do care about the hydronium because that's going to give me pH. It's very important. You ask yourself, what is X representing? For the acid, it's going to be hydronium. For the base, it's going to be hydroxide. Source of careless error. So pH then will be equal to negative log of hydronium ion, which is equal to the negative log of 7.5 times 10 to the negative 6, which is equal to 5.12. Now, I'm not finished yet because I want to ask myself one more question. Does that answer make sense? We said that this was an acidic salt. Is that an acidic pH? The answer is yes. So I have a chance at being correct. Homework 35. Okay, that deals with taking salts and determining the pH of those salts. And once again, very important. You got to be able to do this because this will be part of other reactions when we do neutralization. You will be forming salts, and you will have to do that as part of that neutralization reaction.